Okay, so here we take a look at this sample problem. So it says a figure shows a rectangular loop. Okay, so this one of wire immersed in a non-uniform and varying magnetic field or B field that is perpendicular to and direct into the page. Okay, so the field's magnitude is given by this expression. Okay, so it is related to the time and also related to the x-axis, with b in teslas, t in seconds, x in meter. Okay, the loop has a width w equals 3 meter. Okay, so this is w, and the height h to be 2 meter. So what are the magnitude and direction of the induced EMF around the loop at t equals 0.1 second? Okay, 0.1 second. Okay, so which means that as much as this B field is time varying. Okay, so in such a way the magnetic flux going through this loop is also time varying. So according to Faraday's law, it will generate an induced EMF or induced current. Okay, so first of all, we would like to find what is the magnetic flux going through this loop. Okay, so phi b will be integration of b dot dA. Okay, so and actually the B field is going into the page. Also, this loop you can just simply define this dA to be pointing into the page. So B and dA are parallel to each other and pointing to the same direction. So B dot dA is nothing but B times dA. Okay, so here we can, as much as this B only related to X but not Y. Okay, so Y is a constant for this B field. Okay, so in such a way across the y-axis we can just consider this dA. Okay, so here we have this dA to be this orange rectangle. Okay, originally dA in Cartesian coordinate should be something like dx dy. Yeah, but actually the y-axis is not related to the B field. So finally it comes out to be like something like integration of dy from 0 to h, and then it turns out to be a h. So in such a way we can simply write dA to be h times dx. Dx is actually the width of this rectangle. Okay, so we don't really need to cut this whole rectangle into many small pieces. Okay, we can just consider one strip at one time. Okay, so here this dA is nothing but b times h times dx, something like this. Okay, so and actually this x we will integrate from 0 to w, or 0 to 3 meter. Maybe we can just put it as a 0 to w at the beginning. Okay, so in such a way we can try to substitute the number into it. Okay, so from 0 to 3 meter, and then b is actually having this expression 4 times t squared x squared, and then h is actually this 2 meter, and then dx. Okay, something like this, and then we can just moving the terms that is not related to x to the front. Okay, so here we have a 8t squared, which is not related to x, And then we have an integration of x squared dx from 0 to 3. Okay, so in such a way we have a 8t squared, and then the antiderivative of x squared is nothing but x cubed over 3. X cubed over 3. Okay, so we evaluate from 0 to 3, which means we have a 3 cubed over 3 minus 0 cubed over 3, which is 0. Okay, so it turns out to be like this. So yeah, so it is nothing but 72t squared. Okay, so this is the expression of phi b, the magnetic flux through this loop, and it's actually going into the page. Okay, so in such a way we can use the Faraday's law as the absolute value of E, okay, will be d phi b dt. Or maybe more rigorously, we should also take the absolute value, but we already know that this one should be positive when t is larger than 0. So whether we put this absolute value here is also okay. So anyway, we can just by considering this is a positive and also increasing function, it is nothing but something like this, and then we can plug in this expression here. So we have a d dt and then 72t squared, so which is nothing but 144t. And then here we need to find E, the magnitude of EMF at time t equals 0.1 second, which means E of t equals 0.1 second, okay, which is actually 144 times 0.1, okay, which means we just substitute t by 0.1. Okay, so here we have a 14.4 volt. Okay, this is the magnitude of the induced EMF. And of course we need to determine the direction of this induced EMF using Lenz's law. So in such a way we have a B field pointing into the page and it's increasing, so the B induced should be pointing out of the page according to Lenz's law. So using the right hand rule, you use a thumb pointing out of the page, your other fingers should be somehow like counterclockwise. Okay, yesterday many of you asked, what is clockwise, what is counterclockwise? But I think during the class I have mentioned whether it's clockwise or counterclockwise many times. Okay, so in such a way we know that this is actually counterclockwise. Okay, so the induced current and EMF, or you can say EIND, are counterclockwise. Okay, counterclockwise. Okay, counterclockwise. Okay, any questions? Okay, so here we will talk about the induction and energy transfer. So here we have a simple experimental setup. So here it says a rectangular loop of Y of width L has one end in a uniform external B field that is direct perpendicular into the plane of the loop. Okay, so here you can see this guy is actually holding this current loop, and then the width is L. Okay, so here this is the width, And then here we also have some external B field, okay, showing with this green cross, okay, which means that the external B field is actually pointing into the page. It is actually uniform in this dotted area, okay. Only inside this area we have a uniform B field. Outside it, we assume we don't have any B field. Okay, so this field may be produced by a large electromagnetic magnet. Okay, so the dashed line in the figure shows assume the limits of the B field, and the fringe of the field at its edges is neglected. Okay, so which means no B field outside, and then uniform B field inside this region. Okay, we are to pull this loop to the right at a constant velocity. Okay, so originally this loop is inside this B field, and then we try to pull it out. Okay, so here actually we have some flux change. Okay, so therefore a B field and a conducting loop are in relative motion at speed v. Okay, so we assume we try to grab this loop out of the external B field using with a constant velocity v. Okay, so in such a way, for this current loop, even though the even though the B field does not change, but as much as this loop is moving to the right side, so the phi b is actually varying. Okay, it's actually varying. So actually, this phi b varies as we are pulling this current loop to the right side. Okay, so in such a way there will be magnetic flux changing. So according to Faraday's law, there will be induced B field or induced current. Okay. Okay, so yeah. Okay, so here you can you can see that. Okay, so it says the rate of work is actually the power. 就是这个是 rate of work， 就是单位时间的做工，那功是那个 W 嘛，那就是 dWdt rate of work 就是这个东西，那就是功率power 就是功率。Okay, so it says to pull the loop at a constant velocity v, you must apply a constant force F to the loop because a magnetic force of equal magnitude but opposite direction acts on the loop to oppose you. The rate at which you do work, that is the power, is then given by this expression P equals Fv. So it is somehow like so actually this W generally is somehow like integration of F dot ds. Okay, in mechanics, the work is somehow like F dot ds and then doing a line integral. And as much as we have a P equals dW dt, so it is somehow like d dt, and then we have an integration of F dot ds. So so actually if you just put this thing inside, okay, so it's somehow like F dot ds dt, and actually this ds dt is the velocity. So if the force is constant and the velocity is constant, so it turns out to be a simple product. Otherwise, if it is not that uniform, then it should be somehow like an integral. Okay, so here we try to see what will be the induced EMF. What will be the induced EMF? So here it says to find the current, we first apply Faraday's law when x is the length of the loop. X is the length of the loop. Okay, so here, this is the x. Okay, so we count it from the left edge to the edge of this B field. Okay, so because only this region we will have a B field going through the loop. Okay, and actually, of course, this loop is moving to the right side, so x is actually a constant. It's actually a function of time. It's a function of time. Okay, so yeah, so here this is L, this is X. So the area of the loop still in the field is L times X. L times X. So this area of a rectangle. So then the magnitude of the flux through the loop is phi B equals B times A, because the B is uniform inside this region. Okay, B times A is L times X. Okay, so phi B is B times L times X. Okay. And actually here x is decreasing. X is decreasing because this loop we try to pull it to the right side. Okay, so this x is actually decreasing. The flux also decreases. Okay, Faraday's law tells us that with this flux phi b decrease, flux pointing into the page, and it is decreasing. So in such a way, it should generate some B induced pointing into the page. B induced pointing into the page. Okay, so here we try to use the right hand rule. You use your thumb pointing into the page. Your other fingers will be somehow like clockwise. Okay, clockwise. So which means that this current is from left to right for the top edge, and then from going this way, clockwise. Okay, so here it also tells you that we can write the magnitude of the EMF as this expression. Okay, so here we only consider the magnitude. Okay, so we just ignore the negative side here. So this induced EMF is d phi b dt, and then actually phi b has this expression, so we put the blx here, and actually b is a constant, L is a constant, so we just put it in the front, and then we have a dx dt. We have dx dt is actually the velocity. Okay, so we can write it as a b times L times v. Okay, something like this. So this is actually the expression of the induced EMF. Okay, so the next step is to determine the induced current. So here we just simply use the Ohm's law here. Okay, so I equals E over R. It is somehow like V equals IR. So V equals IR. Okay, this is the Ohm's law. So last week I think I've mentioned that you can consider an EMF is similar to a potential difference. Okay, so this is one of the examples. So V equals IR. Here we also use E equals IR. Okay, so in the previous page, we already know that this E is BL times V. So this I is BL times V over R. Okay, so the deflecting force acting on the three segments of the loop are marked F1, F2, and F3. F1, F2, and F3. Okay, so this is actually according to the Lorentz force. Okay, we learned in chapter 28. Okay, so as much as we have a current carrying wire in B field. Okay, so we should have F equals I L cross B, I L cross B. Okay, so for instance, okay, for the left edge, okay, here for this one, L is pointing upward, following the direction of the current. Okay, and then the B field is pointing into the page, so yeah, pointing upward and then crossing into the page. Yeah, your thumb is pointing to the left side, so F1 pointing to the left side. And then here, this is L, so L cross B, your thumb is pointing upward, okay. And then for this one, L is pointing to the left side, so L cross B, okay, your thumb is pointing downward. So F1, F2, and F3 points to these three directions. Okay, so in such a way you can simply consider these F2 and F3, these F2 and F3 cancels each other. Okay, they are actually the same with the same magnitude but in opposite direction. Okay, so only F1 is the net force acting on this loop. So that's why when you try to pull this loop out of the external B field, so F1 is actually pointing to the opposite direction. So it feels like, okay, there is a force grabbing it backwards. Okay, so this leaves only force 1, and then which is direct opposite your force acting on the limit, force opposing you. Okay, so just as what I mentioned, F is actually ILB times sine of 90 degrees. Okay, so L and B are perpendicular to each other. So this is nothing but I times L times B. And in the previous page, we already know that I is this EMF, BL times V over R. Okay, so this is I times L times B. And then we can collect similar terms. So we have a B square, we have L square, B square L square times V over R. So this is the force or F1 acting on this loop. So finally, we can use this F and then plugging it back to the original definition of the power, the rate of work. Okay, P equals FV. So we also multiply a V to this expression. So finally it becomes B square L square V square over capital R. Okay, so this is the rate of work. Okay, you need to do the work, and the work in unit time, okay, is this value. Okay, so the work that you do in pulling the loop through the B field appears as thermal energy. OK， 所以就是说它就会有电流，然后它有电阻，所以它就会发热啊，它就会发热。OK。Okay, so the next one is called the eddy current. Eddy current in Chinese is 涡电流，就是一个漩涡的意思。涡电流。Okay, so as you pull a solid conducting plate out of a B field, okay, eddy currents are induced in the plate. A typical loop of eddy current is shown. OK， 所以这里的意思是，前面我们是拉一个线圈，线圈的话，那电流就只能沿着那个电线去走嘛。那现在的意思是我拿着一个金属板，我从 D field 拉出来，它还是会有一个电流在里面绕圈圈啊。 那它就标示一个，它可能其中一个的，其实它不只是在这个路径有，其实是像个台风那样，就是其他地方也会有的，不只是这个路径 ，OK， 所以他说typical loop 就是其中一个而已。它的意思也是因为有 B field 的改变，所以它就会产生，所以特别是沿着这个边缘的地方，它就会感受到比较大的那个 magnetic flux change， 所以在这个地方，所以这个圈是集中在这个 B field 的边缘啊，里面的地方就是它好像就是没有什么改变。Okay, so here we will introduce another form of the Faraday's law. So previously we learned the Faraday's law as this one, E equals negative d phi b dt, or we sometimes multiply it by n. Okay, if the loop has n terms, then we just multiply the derivative of the magnetic flux by n, and then take the negative sign on the right side of the Faraday's law. But here we try to write out another expression of the induced EMF using a line integral. So this Faraday's law actually looks like this one. Okay, so on the left side we have an integration of E dot ds. On the right side is still the same, negative d phi b dt, and if there are n terms, you just multiply it by capital N. Okay, so nothing special on the right side. And then on the left side, it is a line integral, somehow similar to the Ampere's law, but the Ampere's law on the left side is integration of B dot ds. So it's the line integral of the B field, here is the line integral of the E field, something like this. Okay, so actually this expression look somehow new, but actually you have seen something similar before. Okay, in chapter 24, you should have learned this electric potential. If you still remember, I think you should still remember because we only have exam yesterday. So the electric potential is actually like V equals negative integration of E dot ds. Yeah, if you still remember. Yeah, so actually this is a line integral for the E field. At that time we don't have any magnetic flux, not mentioning the time varying magnetic flux. Yeah, so and actually at that time when we talk about this electric potential, we tell you that this line integral only relates to the starting point and the end point. Okay, the path itself is not really important. You can choose arbitrary path to finish this line integral. Yeah, as much as it is easy to calculate, then it's okay. It's only related to the two end points. In such a way, if we are only considering the electrostatic and the starting point and the end point are the same thing, turns out to be this one. In that case, this line integral should be a zero. Okay. 那个意思是我们24章学这个 electric potential 的时候，当时是没有 B field， 更没有这个实链的 B field， 所以当时这个线积分的话，只跟起始点跟终点有关，跟中间的路径无关。只要好算，你选一个好算的路径，那你算出正确答案就好了。那所以在那个静电学的场景底下的话，如果我们绕满一圈的话这个圆圈就是说绕满一圈嘛，这是一个 closed 的一个 loop。那绕满一圈，在静电学之下，这个 potential 一定是零。但是现在的不是静电学， 这个是所谓的 EMF 啊，这个是 induced EMF。所以它某些程度跟这个 potential 很像，某些程度不一样啊，某些程度这里就不一样的地方就是，如果它有一个实面的磁场的话，这个绕满一圈的线积分它就不为零，它不为零，它就是这个值，它就是这个值。但是如果是静电学的话，绕满一圈的电场的线积分就一定是零。OK，induced electric field are produced not by static charges but by a changing magnetic flux. Therefore, electric potential has a meaning only for electric field that are produced by static charges. Okay, static charges 就是我所说的那个静电学 electrostatics 的情况，就是只是由电荷来的电场，它这个electric potential 才有物理意义，才有意义。不然的话，你搞混的话，就会算错。因为有时候你就觉得它是零，有时候觉得它是这个东西，那你乱起来的话，就会后面的结果就会错误。那 it has no meaning for electric field that are produced by induction. Okay, so so here how we should use this one is actually similar to the Ampere's law. So I think in chapter 29, okay, we already learned the Ampere's law. So on the left side we have something similar. At that time is integration of E dot ds for a closed loop. Here is integration of E dot ds. So the only difference is for loop, ds is actually the parallel to the tangent line and for the direction of the loop, and then you determine all the E dot ds for every small segment of a path, and then you add them together using an integral. So you rewrite it like this, so I don't try to repeat too much. And here on the right side, a little bit difference is that we have a derivative. We have a derivative on the right side. Okay, so in such a way, for example, we have 1, 2, 3, and 4. We have 1, 2, 3, and 4. So we have several paths. Okay, so it says equal EMF are induced around path 1 and 2. Okay, so this is path 1, this is path 2. Yeah. Okay, so of course here we assume that the B field is pointing into the page and is originally it is uniform, and then it is also changing in a uniform rate. Okay, 就是它一开始的时候它是均匀的，然后它也以一个等比率的方式去改变，就比如说它等比率的去增强 ，OK， 因为它有改变了，就是它有一个time varying 的 B field， 所以它是一开始是均匀，然后它也以等速率的去改变。Okay, so in such a way we have an equal EMF are induced around path 1 and 2. Okay, path 1 and 2. So we just assume that this shape and this shape are the same. So the only difference is that the position are different and the direction are different. But actually it encloses the same area, so it should provide a same EMF. And then for path 3, okay, a smaller EMF because part of the area are outside of the B field. Okay, so we just assume that there is uniform and constant changing B field in this yellow area. Okay, so for path 3, okay, so this d phi b dt is smaller than the path for path 1 and path 2. And for path 4, actually this should be a 0 because it should have no B field and no B field changing for the path 4. So no net EMF induced around path 4. Okay, so this is I think this is easy to understand. Okay, so here we have a sample problem. So in the figure, take R equals 8.5 centimeter, dB dt is 0.13 Tesla per second. Okay, A, find an expression for the magnitude E of the induced E field at points within the B field and radius R from the center to the B field. Evaluate the expression for R equals 5.2 centimeter. Okay, so here for the Faraday's law, we have an integration of E dot ds on the left side and actually with the same argument as we have done in the previous chapter for the Ampere's law. Okay, E field and E field and ds. Ds is actually the tangent line of each point, and then follow the direction of the loop. Okay, so E and ds are parallel to each other and pointing to the same direction. So this is nothing but E times ds, and then also E field is uniform, so we can just put it outside, and then finally integration of ds for loop is nothing but the circumference, 周长, so it's 2 pi r. So all the things is similar to the Ampere's law. Okay, what we done in the previous in the Ampere's law. Okay, so on the right side we have the derivative of the magnetic flux. Okay, so first of all we write out the phi b, okay, the magnetic flux, and then which is b times a. So this is nothing but b times pi r squared. Okay, so it's a circle, the area of a circle, and then we can take the derivative of phi b. So it is actually d dt and then b times a. And actually a is a constant of time. So we can just put it outside, and then we have a dB dt. Okay, so actually it gives you dB dt equal to this value, so we can just make use of it. So it is nothing but 0.13, and then this a is actually pi r squared. Pi r squared. Okay, so in such a way we have an integration of E dot ds equals negative d phi b dt. Okay, so on the left side it is E times 2 pi r according to this one, and then here we have a negative 0.13, so equals negative 0.13 pi r squared. Okay, so here we can do some cancellation. This r cancel with this r square, and then this pi cancel with this pi. So finally we have E equals negative 0.13 over 2, and then times r. Okay, so actually we can just take the absolute value. So E equals 0.13 over 2 r, and then the SI unit should be V over M. Okay, volt per meter. So this is the expression expression of the induced E field in terms of R. And then finally it asks you to evaluate the expression for R equals 5.2 centimeter. So here we have E for R equals 5.2 centimeter. 5.2 centimeter to be 0.13 over 2 times 0.052. Okay, so this is nothing but 3.4 millivolt per meter. Okay, so this is for question A, and then we have a similar one for the question B. Okay, so actually, what we need to pay attention is that the radius of this yellow circle is 8.2 centimeter, and here it asks you the region out of this yellow circle. So it asks you the R at 12.5 centimeter. Okay, so here we just need to do some modification to the d phi b dt. Actually, the left side should be the same thing. Okay, so on the right side, it is nothing but 0.13 pi capital R square. Okay, because we only have time varying B field inside the circle. If you have an ambient loop, and here we have an ambient loop, yeah, greater than it, but this region don't have any B field or time varying B field. Okay, so we only count phi B up to the yellow circle. So which means that this is a capital R rather than a small r. Okay, so and then we can just apply Faraday's law, which is integration of E dot ds equals negative d phi b dt. Okay, so on the left side it is E times 2 pi r, and then on the right side negative 0.13 pi capital R square. Okay, so here we can only cancel pi. Okay, in such a way E is actually negative 0.13 over 2, and then R capital R square over small r. Okay, so actually this is the closed form solution, and or you can also take the absolute you can also take the absolute value. You can also take the absolute value as the absolute value of E is 0.13 over 2, and then times capital R square over R. Okay, so this is the closed form expression. And we try to evaluate this E at R equals 12.5 centimeter. Okay, so here we just need to plug in the number 0.13 over 2 times this is 0.085 square over 0.125. Okay, so this is 3.8 millivolt per meter. Okay, the values are similar.